What I'm going to talk about today are milk peptides and enhancing their function in food. So I'm just going to outline some of the health benefits of the milk peptides, why we're studying them, then looking at the challenges of protecting them within a food system, and then just talking about some of the systems that we've developed within a program here at UCD to protect those peptides. So looking at some of the background, in terms of what's happening in the Irish landscape, I suppose it's very important that within a matter of months we're going to see the end of the European milk quotas. And in response to that, many of the dairy industries are really ramping up their production of milk, because we do have the overall aim of increasing the volume of milk we're producing by 50% by the year 2020. So increasing the volume of milk comes obviously with its own challenges and processing challenges, but I suppose there's this bigger issue is in how do we realise value from having increased that volume of milk. So there are a number of initiatives at a national level to try and look at this area. One of those is Food for Health Ireland, which was a programme set up to try and add value to milk ingredients. And I'm calling it a milk peptide program because for the most part the focus is on the protein element of the milk, although there are other elements headed up within Teagasc from an infant formula point of view that look at other aspects, but the vast majority of the program is on milk peptides. And what this program is planning to do, and it's now in its 6th year, so a lot of the work is already well underway, is trying to extract compounds from milk, largely from a protein element, screen those proteins in terms of their efficacy from an infant formula point of view, metabolic health, sports nutrition, and also muscle performance. Both ties in the sports performance, but also from an elderly point of view with declining muscle mass as we age. There's also a food technology pillar within it, food formulation element, and I suppose a key part of it in terms of this research program, which may differ from other research programs, we are looking for end products that are commercializable and that will go into the marketplace. So it has to go all the way from the bench right out to the marketplace, and that brings its challenges with it. So some of what I'm presenting today is talking about those challenges of trying to translate something from laboratory research into the marketplace. So essentially what the program is hoping to do is design foods to keep healthy people healthy. And it is, as you saw there in the first slide, right across the life cycle. So for example, in the current tranche of the program, we're looking at pregnant mothers and trying to see, can you intervene from a dietary point of view to improve not only the status of health for the mother, but the fetus, and ultimately how that child is going to develop its health throughout its lifestyle, and then all the way through to the elderly cohort. So it is spanning the full life cycle. What do we want to achieve? We do want to achieve food, just to stress that. So we have to have ingredients that are capable of being delivered in food systems. And if we to look at, I suppose, what the companies see success as, it really is having foods that is going to have a real impact as we put them into human trials. So it has to be very measurable from a human nutrition perspective. Why are we looking at milk? Well, I've mentioned earlier there is the economical side of it, but that's not really the driver as to why milk was chosen. Milk is very elaborately studied. We can see some of the presentations here today where we have an intricate knowledge of what's going on in the milk system. The protein system is particularly well understood. And since milk really is the only source of nourishment for the first 6 months of a human life, and similarly for different time spans within mammals, it is an obvious place to start looking for biologically active compounds. So it made a lot of sense to start with milk. And I probably should have mentioned at the start that its 5 dairy companies sponsor the research as well, and they want to keep the focus on the dairy area. In terms of how the peptides are generated from milk, there are a number of techniques that are used. The first and probably most of the samples we receive are generated by enzymatic hydrolysis of the proteins using digestive enzymes. There are also microbial fermentates largely produced in the Chaga site from Moore Park. And then within the program, we look at peptides that are naturally developing during cheese ripening. And of course, fermented milks, it's not part of this program, can be a source of these peptides also. So the peptides can come from a range of sources. But for those who may not be familiar with the notion of protein hydrolysis, and this is not representative of a milk system, it's just totally schematic here. What we're talking about at the end of the day, whether it's enzymes or whether it's the digestive enzymes, microbial enzymes or cheese, what we're talking about is the breakdown of the protein either within the protein by the enzymes, or it can be just the terminal components of the protein. So these are representing component amino acids in the protein. So we're cleaving peptide bonds to generate material that is a smaller molecular weight. And as a result of that, you see different activity, particularly from a health promotion point of view. If you look at the literature, it really is awash with evidence of showing that the peptides have health benefits, really to varying degrees of efficacy. Some of the work really is just done at a very basic level within a laboratory, and there aren't human studies going with it, or there aren't even animal studies going with it. But just to set the scene for you, there is quite good evidence to suggest that the milk peptides can reduce blood pressure, can reduce blood cholesterol. They've also been associated with weight management, particularly having the ability to increase the feeling of fullness and satiety, and perhaps long-term being able to control appetite. They've been shown to stimulate the immune system. There's quite strong evidence in the role of the peptides in terms of dental health, particularly in being able to decrease the main pathogen that causes dental caries in humans. And then more recently, you will be aware, I suppose, a lot of the whey protein-based products that have been associated with muscle building, muscle recovery, and the bioactives in combination, that maybe the peptides with these proteins can have quite a beneficial effect in this whole sporting arena. So there was quite a lot of evidence, I suppose, from a health point of view as we began. And then I said the difference in this program is that we are trying to get a product that will be commercially viable and that we can put into food products. So we can't just stay at the laboratory end of it. And a key challenge in using some of the milk peptides, if you get them into functional foods, one is that the peptides are highly reactive. Proteins, by their nature, do lots of great functions in food. So therefore, they interact with lots of the ingredients. So we have to ensure that if they want to keep the peptide to have its health benefit, how do we prevent it interacting with components in the food matrix that may cause it to lose its efficacy? In addition, proteins are designed for us to be able to digest them. So therefore, as the proteins are consumed, we begin digestion in the mouth, and then as we pass through the stomach and the small intestine, etc., there is always a danger of losing the efficacy of these peptides. So they may have been very good when you tested them in your lab scale process, but by the time we consume them, we can lose the efficacy. Not all of the time, but a lot of the time. The other challenge in putting milk peptides into food is that they really aren't the most palatable of ingredients. I'm not going to focus it in this talk, but this is taken from some principal component analysis done on the Food for Health Ireland hydrolysates and also commercial hydrolysates. And these are the key elements that are coming out. So the two key taste elements are bitter and astringency, neither of which is very attractive to any consumer. And then you can see from aroma point of view with the whole series of terms that are there. Again, a sulphurous, wet dog smell, not really particularly appealing. So with these main technical challenges, we were looking for solutions. Is there a way around of trying to stop the peptide interact with the food matrix, can you curb the digestion of it, and can you do something from a taste point of view? And one approach to this is looking at encapsulation in order to undertake all of these 3 protective mechanisms. So what I'm going to talk to you about is some of the systems that have been developed during the course of the program. For those of you who may not be familiar with the concept of encapsulation, and in fact it may not even be the correct term in terms of the systems that I'm going to talk about, maybe entrapment is a better way of describing it. But in terms of encapsulation, what we're trying to have is some type of protective matrix around the milk peptide or the bioactive. So essentially you're trying to screen, so if the little blue bit here is going to be your active milk component, you're trying to make sure that this is protective. So for example, this would be some type of matrix, then I'll describe some examples of where those matrices come from, and you're trapping the bioactive in here so that it's not going to be as reactive. From a food point of view, there's a limit to what the consumer is going to pay for functional foods. Okay, it's not like drug discovery, that if you're going to have a drug that's going to alleviate cancer or cure cancer even, then you will pay quite a lot of money for that. In food, it's about keeping healthy people healthy. So there is a limit to the margins, and as a result, there's a limit to the types of techniques we can use for these procedures. So for the most part, it's important to try and use technologies that the food industries can adapt and upscale fairly readily. So the common techniques that would be used would be those used for producing many ingredients within the food system: extrusion, fluid bed coating, emulsification, or spray drying. And then the types of materials tend to be hydrocolloids, so proteins will be one, carbohydrates, and then it's often mixtures of proteins and carbohydrates and lipids, or in fact lipids by themselves can also be used. So in what I'm going to describe is that we began by looking at one of the systems we looked at, which is all I'm going to focus on today, is food proteins as the encapsulant. Again, because of the fact that it was going to be label friendly in terms of the end product that we were going to use, and they would be digestible because we do eventually want release of the bioactives. So in a perfect world, what would the perfect protective system look like? First of all, as I just said, it really needs to be a low-cost substrate and a low-cost technology, okay, if it's going to be viable within a functional food arena. You have to be able to efficiently load the matrix with the sensitive peptide. Okay, you can't end up in a situation where the protective coating is more expensive than what you were trying to protect in the first place. So cost is a major element within it. It needs to be stable within the food system, and then you need to have controlled release within the digestive system so that you maximize its efficiency when we consume the product. So that's what we're looking for in an ideal world. And the system I'm going to talk about just quite briefly today, and giving an overview of a number of the PhDs that were conducted in this area, is based on whey protein gels. So the basic underlying principle of the system was that we're taking a commercial whey protein. I mean, this is showing it in its unaggregated native protein, this model system. Obviously what we get from a commercial system isn't purely in its globular state. We heat it very carefully to aggregate it into these type of fibrillar structures, and then cool it down either through pH adjustments or salt adjustments to get these aggregated filaments. And the concept then being that we trap the bioactive within these aggregated filaments that we form. We took a number of approaches to it. The first is just showing the production of whey beads. I'm using the term external gelation here because you're taking the denatured whey protein, dropping it into a calcium chloride solution, and the calcium chloride you've an external bath of calcium chloride. It reacts with the whey protein and you get little beads formed. A second approach taken, we've called it the internal gelation process. And in this case, again, you're starting with denatured whey protein, but in this case, what you have is calcium carbonate as part of the whey protein. You're dropping it into an oil phase. You're then using acid to release the calcium inside the whey protein, so you're gelling this from the inside, so therefore it's called internal gelation. And using the two methods, you get these little whey beads. So in the internal you're getting quite small beads down to 20 micron, and you can be up to 2 micron depending on the methodologies used. I won't go into the details of this here, but just one of the challenges we had was to keep the beads stable within a food environment. And these are some of the outcomes that we had, that they did show very good resistance to pH, the normal pHs you'd see within a food system, within resistance to the temperatures you might use in processing, shearing conditions, etc. And we were able to use them for encapsulation of whether it was something that was like a lipid. So if you want to encapsulate an unsaturated fatty acid, for example, or whether you wanted a water-soluble bioactive. So they were showing good versatility. Again, I won't focus too much on the detail of the results here, but stability within a food product is important. And having tested the beads at a range of pHs and temperatures, we were seeing particularly good stability at 4 degrees at a pH 4.5. over quite a long time period. So for example, we knew that they could go into something like a yogurt or a fermented food product. So we were, I suppose, getting the stability within a food system that we wanted. So that was the first bit of the box ticked. The next bit was I suppose, to look at how those structures break down within the intestine. And this is a very, very simplistic model of digestion. So you're just looking at a combination of pHs and enzymes that in some way simulate, in the first case, gastric digestion, and then as you move into intestinal digestion. And just to note, I suppose, that in this case here, by having changes in the bead matrix, by adding oil into the whey beads, we see quite a big change in how the bead breaks down and in what release of bioactives we're getting. So again, just pointing to the difference here, the triangles here have 20% oil, and the 0% oil is up here. So in terms of the matrix digestion, you're slowing it in the presence of oil. Similarly, when you look at the bioactive release, the oil is releasing this. So it's an important finding that if you're going to formulate a food, that if you have some fat there, you may slow down the release of the bioactives. So in going from an encapsulating system to formulating a food, this is giving us good guidance as to what we might need to do. So for that part of the work, what we're seeing is we can produce water-insoluble microbeads. They're very stable within a food system. And the incorporation of lipids into the beads is giving us quite good control over how the beads might break down and how they might release the bioactives. So they're showing potential for sustained release of bioactives, and we had work to show that you could apply them to a charged bioactive or a hydrophobic bioactive. But I suppose trying to look at the practicalities of the type of the program that we were working with, we wanted to see, could you use those beads in a different way to what would have been the traditional approach, which is what I just presented. And it was to see, could the beads be used as sorbents? So could you create blank beads and then get the various bioactives absorbed into them? So just using a schematic to explain that to you. So the traditional method is shown there on the left that I just described, that you taking a whey protein, you would mix that with the bioactive, drop it into this calcium bath, which will form the bead. And if your bioactive is a large bioactive that stays inside here, then life is good, that's fine. And if you get immediate gelling of the whey protein. But in reality, when you're using this method, when the bioactive is inside the whey protein, there's always the danger that while you're setting up the bead, that you lose some of the bioactive, or that subsequently you just get some diffusion of the bioactive in. So the question we were posing is, if you made the beads without any bioactive and then put them in, and basically to see could they act almost like a sponge type of structure, could they absorb the bioactive, and would that be a better approach to take. The advantage of this as well, in going through the formation of the bead, I'm skipping over a lot of the technical details, it can be quite difficult to control this process. So every time you add a bioactive in there, then you could begin to change how the bead is forming, which is making it all more complicated. Okay, so in taking this approach of having a sorbent method versus the traditional method, what we found is we could get much more bioactives into the system. So we moved to taking this approach to the encapsulation. Again, within the Food for Health Ireland programme, I'm talking about peptides, but in fact, we don't get peptides from the people that generate the bioactives. What we get are hydrolysates, which are a whole mixture, which may have intact protein, small peptides, large peptides, peptides of all different sources. So we're trying to see, would this ever be applicable to the very complicated hydrolysates that are coming towards us? So we try to see, would it be applicable to, for example, very charged peptides. So again, we were trying to simplify matters by saying, could you predict as to how useful the system would be for charged bioactives? And the first model that was set up here was to see if, based on the ionization profile of the whey protein that we were using to make the beads and whatever the bioactive made, could you predict where you were going to get the best binding, which you would expect to be obviously where there would be largest charge difference between the two. Okay, in terms of what we found with the very, very high, simplistic model of a charged amino acid, histidine, the dots are the experimental work, and then the dotted line is the predicted data, that we were getting very good correlation between them. But this is only single amino acid. When we moved to a charged peptide, a cationic peptide, fit isn't quite as good, but you are seeing there's very good correlation where you're getting maximum interaction. And then similarly for the anionic peptide, again, good correlation between where you're getting maximum interaction between the bead and the charged peptide. So overall, we were seeing you're getting good protection of where you're going to get maximum interaction between the peptide and the bead, which gives us a good starting point as to how we would load the beads in the best way possible. Again, it comes with the caveat that this is a model peptide with 5 amino acids, and we're trying to deal with very complex hydrolysates, but it's a starting point. Again, looking to see if it was going to suit hydrophobic entities, we looked at hydrophobic amino acids working up to hydrophobic peptides, and you're seeing we're getting more encapsulation the more hydrophobic the peptide is. So hydrophobicity seemed to be driving the system in terms of the encapsulation. Okay, in dealing with the real world, we had to see, was this an efficient process? So looking at the kinetics, we're seeing that you do get encapsulation in almost all of the variables we looked at. You're getting maximum uptake within 20 minutes. The more beads we put into the system isn't really helping the rate at which we're taking up the bioactives, but as you go and put more beads into the system here, you can see at the highest level you're getting most peptide in. So you can load up the system to try and maximize the efficiency and to get the beads taking up more of the bioactives. Then moving this to the digestion end of things, and I suppose the only curve that really is of significance in this is the one where it's in some way mimicking the digestive system, where you're at a low pH and you have gastric enzymes present, and we're looking at the release of a vitamin from the system. And you can see you certainly are getting breakdown of the bead and release of the bioactive. We do want release of the bioactive. There's no point if it's going to make its way all the way to the colon, but it's perhaps faster than what we would have wanted and not fully optimized. So we're getting some control, but not the control we would have wanted. And then very simply, this curve is showing that by taking those beads and drying them, we really are slowing down the rate of release and the amount of material that's being released. So again, it's quite a simple step from a processing point of view, but slowing down and getting us nearer the controlled release that we want. I mentioned that these are very, very simplistic digestive models and really wouldn't be expected to be most predictive of what might happen in a human system. So the next step we took was to put it into an animal study. So it's taking these beads, loaded with the vitamin, feeding them to piglets. The pigs were catheterized so that we could take bloods at regular samples and see what type of release were at regular time intervals to see what kind of release will we get, and then analysis was done on the blood. Again, it's not a fully powered study, but it's indicative of what results we might get, and there's more replicates needed on this study to validate the results. Okay, in doing the study, we also recovered the beads from the digestive tract of the pigs. Okay, so at the top there you have, this is the bead, the dried bead, which was showing the slowest release in the laboratory work. And this is showing the beads after 1, 3, 6 and up to 8 hours post-ingestion, and then taking samples from various parts of the digestive tract. And you can see for the most part the beads do stay intact until you're down to the very end of the digestion system. But having the beads staying intact doesn't necessarily mean that it's working, because all of the bioactive you put in there could long since be gone. So the bead could be there, but the bioactive could have gone at the stomach level of ingestion. So then looking at the blood plasma results, what you can see here is, so these are the blank microbeads that would be fed to the pigs, so they didn't contain any bioactive. This is riboflavin, or the vitamin put in an unprotected state. And this is the riboflavin that was protected by the beads. And you can see over the time course of the experiment that the plasma levels for the vitamin B were higher for the beads that were or the riboflavin that was protected within the beads. So we are getting the type of response that we were hoping for, and it has, this in vivo trial was in some way mimicking the in vitro results that we got. So it's positive from an animal trial point of view. So to summarize it, the blank whey microbeads can be readily prepared, and it gives us much better versatility than using the traditional method of putting the bioactive into the forming solution. They were used successfully for protecting vitamins and peptides. We did see a greater level of uptake with hydrophobic peptides, the more hydrophobic the peptide that we got. And the simple step of drying the beads did improve the rate of release that we were getting and gave us better control over the system. In terms of, is our in vitro model correlating? Yeah, it looks quite positive in terms of the animal trial, but as to say, we do need to do more thorough results, or more thorough investigations of that. And we did see protective effect from the encapsulating systems that we were used. And I suppose to get to the final line there, and I've put it in red saying dried whey proteins, microbeads, are they good structures for the protectant of milk protein hydrolysates? The work where we are to date has really only dealt with peptides, very controlled peptides, model peptides. So there really is a large body of work done to further extend this into the hydrolysates. The learnings that we have, we may not be working with the exact beads that you've seen, but from the chemistry of it, we are quite hopeful with some of the further work we've doing that we can get a very good interactive system with the whey protein system, perhaps with some lipids there also, and the hydrolysates that are being supplied by other members of the FHI team. So it is a particularly challenging project, as I say, in order to also have something that is going to give a bland taste. And while I haven't focused it on here, initial studies with the beads would suggest that you are getting a protective effect. Because they're insoluble in the mouth, we can't taste them. So we can overcome the taste element. We are getting controlled release. But I say there is a further challenge in applying this into the very complex hydrolysates that are generated within the overall program. So we have made progress, but the overall aim of the project is to have peptide-enriched foods that will be used to maintain health throughout the generations. This is just one part of it. It's a positive step in the right direction, but a lot more work to be done in the next few years. Just to thank the people who did most of the contributing to this work, it's particularly Graham and Thelma. The results are taken from their PhDs. Since we were talking about careers, they've actually taken very different career paths. Graham has gone on to Accenture to do data analytics, and Thelma is involved in a different type of analytics, more chromatography analytics with Kerry Ingredients in NACE. The work was supervised by Mick O'Sullivan and JC Jacquier, and then Nessa Narhona, who's the overall manager for the FHI programme, tries to make sure that we keep all the work relevant to Food for Health Ireland, and that we don't get too caught up in academic curiosity that goes with this programme. So these are the people that did all the work, so to thank them, and thank you for your attention.